All right, so this is force 1. We're going to solutions to about it. All right, so we look at the pair of the objects. We want to know which one has. Looking at it, what's really important inertia is. Inertia is an object's motion. The way we talk about that, mass. So if I want to know an object's inertia, all I'm asking for the more mass I have, inertia I have. To do with its motion, more mass we've got, the more. When we go through each of these, freight train or car has more mass, train has more inertia. Long ball or baseball, baseball has more mass. Fast bowling ball or a slow bowling, same. Motion is unimportant for how we measure inertia. The 20 kilogram mass has more mass, so more inertia. Rock on Earth or rock in space, well, same mass. Bowling ball, that it's not the same. For a fast baseball or a bowling ball at rest, bowling ball. Here's the big idea. Mass is the same thing as inertia. It does not depend on force acting on the object or the motion of the object. Do with how much you have. 2. Identify the following forces of applied tension, weight, friction, or normal force. All right, so the applied force is just you pushing or pulling. You do. Tension is the pull from a string. Get tension. Weight is the gravity. Normal force is a surface force. Normal force, not anything else. Always perpendicular. Perpendicular. Go through these. Force that's due to a string is tension. Force that opposes weight for objects on surface. If we're on a surface and it's pointing in the direction opposite weight, it's going to be normal force. You push down on an object, this force increases when it's on a table. It's going to be the normal force. Normal force is a measure of how hard two surfaces are being pressed into one another. Weight is caused by gravity. When we do gravity, I always want to do mg because that's how we're going to decrease on the moon. That's going to be the force of gravity. What decreases the surface is smooth. Works. Put a heavy object on a board and the board breaks. If it's normal force is a surface's ability to support an object. If you do that, you exceed the normal force, maximum available. It's going to break. And it's always vertical. Gravity. Weight is always vertical. I tilt a surface, the direction that's perpendicular to the surface change. Surface perpendicular force changes as well. All of the forces have units of newtons, all forces, and the normal force does not exist for hanging objects. If we're not resting on a surface, then we do not have a normal. So when a net force, when a single force is acting on an object, all knowing what these forces are help when we are drawing a free body diagram. That's why we spent the time going. All the forces acting on an object, list 3 things that could explain why. One thing that can happen is that we speed up, down, direction. Now, turning, we turn, it's going to be something a little bit different. So, speeding up, that's when my force is in the direction of motion. Get faster. Pushing something forward and it speeds up. Slow down, when my force is against the direction of motion. And changing direction, that happens when my force is perpendicular. This is all Newton's second law. Objects will accelerate when force acts on them. That's what's going on. All right. Questions 4 through 7 have us calculating the net force. When we talk about net force, what we want to do is add the forces together, but their direction matters. Mass 1, net force, 30 newtons minus 25 newtons. That net force is 5 newtons, but it's pointing in the backwards direction. Second one, it's 15 newtons minus 15 newtons because they're in an opposite direction. Force of 0. For the last one, the net force is going to be 8 newtons minus 6 newtons. Net force is 2 newtons. Important about mass 1 is that 5 newtons points to the left. That's the negative direction. Mass 2, there's no acceleration. And mass 3, that 2 newtons points to the right. So, question 7 is going to ask how these masses behave and why. So we'll go through that. Which one could be at rest? They all could be at rest. It's tough. If mass 1 is changing direction, it's going to be temporarily at rest as it accelerates. Mass 2, if it's at rest, is going to stay at rest. Mass 3, if it's at rest, just like mass 1, would be changing direction. They could be turning around, changing direction. All right, for the acceleration is negative. The acceleration is in the direction of the net force. Negative direction is to the left. So if we're left, the acceleration is going to be with the net force. Points to the left. It's going to be negative. Acceleration is positive. That's mass 3. It's the opposite of what's going on, right? That acceleration is pointing in the positive direction. Okay. Has a net force of 0 acting on it? Well, that's the one we solved that has a net force of 0. Picture for that. 0. Has a net force not equal to 0. That's what that symbol is. Mass 1 and mass 3. Balanced forces. Balanced forces is another way of saying the net force is equal to 0. Down balanced force. Net. Could be changing direction. Again, that's mass 1 or mass 2. Type of acceleration. Changing direction, we're accelerating. If we're changing direction, we rest. That's going on with part A. We're accelerating. If we're what happens if unbalanced forces? Again, that's 1 and 3. 1 and 3 accelerate. 1 and 3 have a non-zero net force. That means their forces are unbalanced. Could be moving at a constant speed. The only one that's true for is 2. If we're moving at a constant speed, then the net force. Net force is 0. This is a little combination you need to remember. Acceleration is speed. It's constant. Could be slowing down to the left. So here's the deal. That moving to the left and slowing down. If we're moving to the left, the force would have to be opposite the direction. To the left. All right, so the next one, imagine a giant air hockey table that's several miles long. Disc is going to do after we've pushed it, and it's so if there's truly no friction on this, it's going to go forever. There are no forces to slow it down, no net force, no acceleration, constant velocity. Because there's no friction, what will the speed be after? There's no friction. 0, there's no acceleration. If the disk comes to a stop, some force had to act on it. Must be either some friction that we didn't know about or somebody stepped on it. Some force had to act on it. That force is 0. For it to stop, there has to be 0 net. Be some force. All right. The ball and the cart. I don't love how this question's working. We did with the ball box. If I all of a sudden turn to the right, the ball is going to stay there and the tray is going to move out from underneath of it. That's what's. The ball stays in place because of its inertia. The cart moves underneath. All right, so for each of these, I want to find the acceleration. Take the net force, which is what the man is doing, divided by the mass. We'll go through and we'll do that first. Net force divided by the mass. Net force is 50 newtons. Mass is 10 kilograms. The first one accelerates at 5 meters per second. The second, that's the man doubles his force. That's the second one. 100 newtons divided by 10 meters per second. B, that's when the mass of the object is halved. 100 newtons divided by 5 kilograms. There now is 20 meters. So we're going to take that and we're going to come up with things. If I double the applied force, acceleration doubles. If I half the mass, the acceleration doubles. By 4 times force, I get 4 times the acceleration. If I double the mass of the object, the acceleration would be by 1.